Hello everyone, and welcome to our next geology topic, Earth materials. In this section we're going to learn a lot about the rocks that make up the Earth, and of course the rocks are made from minerals, and so we'll learn a lot about minerals, and then how are the minerals put together and what elements that are in them matters as well, so we'll talk a little bit about the chemistry behind it. Let's start our journey through Earth materials with basics about matter, the atom, and how they're arranged. Matter is any object made by particles or atoms that takes up space and has mass. Matter has chemical properties and reacts to other substances, and it has physical properties such as density, hardness, color, etc. We know that matter comes in three basic forms: solids, liquids, and gases, and then a special sort of matter state, a supercompressed gas known as plasma we see in the sun. Essentially that's kind of a gas as well. So three major states. Matter, to be summed up, is just the amount of, or basically any object that has space and takes up mass. The three forms of matter, solids, liquids, and gases, have properties that we kind of know and understand intuitively. Solids have a definite shape and volume. The particles are very packed together. They have little motion around one another, but they still do have little motion. It's called Brownian motion. The temperature of any kind of state of matter is the amount of molecular motion, and so even solids have a little bit of that, even though it's low energy. Liquids don't really have a definite shape, but they do have a definite volume, and the particles are moving fast enough to kind of break that solid connection that they had before. And gases have no definite shape or volume, and the particles are moving faster than they would be in liquids and solids due to the higher temperatures than they're moving around. The air is an example of gases, mostly nitrogen and oxygen. When you take deep breath in, it's mostly nitrogen and oxygen coming in.
There are 118 known elements, about 92 found in nature. An element is a substance that can't be broken down into any simpler substance. As it turns out, only about 8 elements make up about 98% of the Earth's crust. As you can see the pie graph below, the most abundant element in the Earth's crust is oxygen. The most abundant, oxygen at 47%. The second most abundant, silicon at 28%. And then there are smaller amounts of others. Oxygen, actually, if you stack about 4 of them together in a pyramid shape, silicon fits perfectly right in the center. And so this is a natural fit, and as a result, most rocks are actually made of this kind of base. They're called silicates. But when you add different amounts of aluminum, iron, calcium, sodium, potassium, and magnesium, you get different rock forms, and that represents the different elements you see here.
The atom is the basic unit of all matter. It's made up of three particles: the proton, the neutron, and the electron. The proton and the neutron being in the nucleus, or the proton is the positive one and the neutron's a neutral one. The electron has essentially no mass, and it orbits the nucleus in the electron cloud. Here's a look at the nucleus and the electron cloud, the nucleus being the central core where the neutrons and protons preside. It has an overall positive charge then, and the electron cloud has an overall negative charge. An atom is held together due to electrical attraction. Like charges repel each other and opposite particles attract. This is why the protons in a nucleus attract electrons, and those electrons stay orbiting around the protons. The overall charge then of each atom is 0 because all the electrons are balanced with all the protons. The atomic number is the number of protons in an atom, and this really determines what element you have. The mass number is the amount of protons and neutrons in the nucleus, because those both have mass, but the electrons do not. And as it turns out, there are several different kinds of the same element, and so the average of all the different kinds of elements within a particular group is summed up in the atomic mass, which is the total average mass of the protons and neutrons in all types of an atom. What does it mean to have all types of an atom? Well, those are the isotopes. Let's talk about those next. Isotopes are the same kind of atom, but different arrangements. So they're all the same element with different numbers of neutrons. Essentially, this is an isotope. Same number of protons, different numbers of neutrons. They also then are going to have different mass numbers because the mass number is how many protons and neutrons are in the nucleus. So, for example, protium is hydrogen 1. That has 1 proton. Hydrogen 2 would be deuterium. It has a 1 proton and 1 neutron. Still hydrogen because it has that 1 proton, but it has an extra neutron. Both of those are stable in nature. And then tritium. Tritium is hydrogen 3. It means that the mass number is 3 and the atomic number is still 1. The atomic number is representing 1 proton, and the atomic mass number is the amount of neutrons and protons, and that totals 3 in tritium. If you average all the hydrogen 1s, 2s, and 3s out there together, you're going to get the overall averaged atomic mass of that element. Most hydrogens are protium, hydrogen 1, but there are rare exceptions where you find deuterium and tritium. Tritium is actually radioactive, so we call it a radioisotope. Radioisotopes are those that have an unstable nuclei and give off then radiation. Essentially, nature prefers certain forms, and if an atom's nucleus does not set with one of those forms, it has to get rid of something in order to become more stable. And this makes it a radioisotope. Radiation is basically just that atom kicking out different things in order to become more stable. Radiation reduces the number of protons and neutrons, making a different and stable element. An example would be like uranium reducing down to lead. Uranium has an unstable nuclei form in nature, and so nature says, uranium, you got to get some stuff out of there to make yourself more stable, and so it kicks a bunch of different things out. It'll kick out protons and neutrons, and it'll kick out energy forms in order to get itself to a more stable form, and its resulting stable form is lead. Carbon is used an example here as well. Carbon has stable forms of carbon-12 and carbon-13, but carbon-14 is an unstable form of in nature. Thus, it is a radioisotope, and so carbon-14 has a couple of extra neutrons, and it's got to get rid of those in order to become more stable. There is a shorthand way to write the various isotopes of an element. It's by giving the atomic symbol and then mass number after it. So hydrogen, for example, has the atomic symbol of H. If you then give the mass number of hydrogen, it is hydrogen 2 or H-2. Oxygen also has that. If you give the symbol for oxygen and then give this mass number, it's oxygen-18. That would indicate that there are 8 protons and 10 neutrons in that oxygen. Perhaps a better way to do it, though, is to give the mass number in the upper left of the symbol and the atomic number in the lower left of the symbol. If you look at the bottom examples here, hydrogen, if having a atomic number of 1, indicating there's 1 proton, it can tell us then the mass number is 2. That means that 2 minus 1 equals 1, or 1 neutron. Oxygen 18, written in this form, would give us an 8 for the number of protons in the lower left and a mass number of 18 in the upper left. And if you subtract 18 from 8, 8 from 18, you're going to get 10, and that's the number of neutrons. So this is a better way to write it to indicate what's going on. But these are the different isotopes of elements, different kinds of the same element. Discuss now the periodic table and how these elements are organized, and it helps us then to study them more effectively. As you can see here, there is the periodic table of elements. 92 found in nature, 118 known elements. The periodic table you see is colored to help give you a better indication of what kinds of things lie where, and we'll discuss this in the next few slides.
So as we said before, the periodic table is a way to arrange elements. really in the different columns you have different elements with similar properties, and also in the different rows you have different elements with the same properties. The columns are called groups or families. There are 18 of them, and the horizontal rows, those are called periods. In general, we see that the metals are on the left side of the periodic table and the nonmetals are on the right side. There's a transition line that separates the metals from the nonmetals. In this diagram here, you can see the aqua blue there is separated from the lime green. Those are the two sides of the transition line. It's a line that separates the metals from the nonmetals. And then the metalloids are the ones that actually are in contact with that transition line. Boron, aluminum, silicon, germanium, astatine, antimony, beryllium, etc. Those are the elements that are the metalloids. And then as a special note, group 18 there, those are the noble gases, and those are elements that are specifically very stable in nature and actually don't react with other substances because their electrons are all set with their protons. They're very stable atoms. We'll talk more about that in a little bit when we talk about bonding. Properties of metals. Basic properties are that they're shiny, they're ductile and malleable, meaning you can kind of stretch them around and move them around. They're malleable, meaning they can be flattened out into thin sheets, or ductile, stretched out into thin wires. Copper, of course, is an example of a ductile element, and aluminum can be an example of a malleable element, or elements like that. Iron as well. They are also conductive. They can move electricity. Electrons can flow freely through them because of their internal chemical makeup. Nonmetals are typically dull. They don't conduct electricity, and they're also brittle, and they aren't able to be pounded out into any kind of thin sheets or drawn out into wires or anything. Metalloids are a combination of both metals and nonmetals. Different various metal properties can be combined with different nonmetal properties to make metalloids. For example, silicon is a metalloid. It's also a semiconductor. It's not fully able to conduct electricity, but it does so in a partial sense, which makes it very useful for computer chips. Let's discuss how matter combines, because it really then is going to take us into how minerals are formed. Matter is everything that takes up space and has mass, and it can be actually subdivided into a couple of categories. Elements, which are just the basic unit of all matter. You can't separate those down into anything simpler. The basic unit of an element then is an atom. Compounds are a couple of elements or several elements combined together to make one unique thing. The basic unit of a compound then is a molecule. An example of that would be sodium and chlorine combined to form salt, and that molecule then is NaCl, repeating units of sodium and chlorine. And actually that's a cubic structure, believe it or not. Mixtures are a physical combination of elements and compounds. So two compounds, NaCl and H2O, can combine to form salt water. You can actually, though, separate those by physical means, such as evaporating the water away and leaving the salt behind. So that's kind of the differences there between the different kinds of matter and how they're arranged. Compounds are, as we said before, atoms of two or more elements combined. Water is an example. It cannot be separated by physical means, but it can be separated chemically. The molecule then is the smallest unit of this. A mixture then is the two substances that cannot be chemically combined and can be physically separated. Salt and water, we talked about, was one example. A more simple example might be a bowl of M&Ms and Skittles put together. You can separate those out. A solution is a mixture in which one or more substances are uniformly distributed in one another. So salt water was an example of a mixture. Another example of a mixture that's a solution besides salt and water would be alloys, like steel. Steel is a solution in that it's a mixture of two or more metals that are evenly distributed throughout. These chemical elements have a tendency to bond as a direct result of how the electrons are behaving in the energy levels around the atom. Every element has one basic energy level, and that's its ground state. It's where the electrons are closest to the nucleus. And because that level is such a smaller level, only 2 electrons can fit in that level. After that first level around an element, each of the electron levels can be filled with 8 electrons. So you see in this example here, we have the nucleus in red. The first electron energy level has 2 electrons, and each successive energy level out from that first level can hold 8 electrons. Now, the reason we're talking about this is because it becomes important when elements actually bond. And of course, bonding of elements produces our minerals. So, here's how this works. If 1, 2, or 3 electrons are in the outer level, electrons have a tendency to be given up easily. And if 4, 5, 6, or 7 electrons are in the outer level, then the atom usually takes on more electrons. What the element wants is to have its outer shell, whatever it is the outer electron energy level, it wants that completely filled with electrons. Elements have a tendency to form this because nature prefers this. That's why the noble gases are such stable elements. If you look at helium, it has 2 electrons in its outer shell, and that happens to be the first energy level. And so every electron that could possibly be present in that energy level is present, and that element then is stable. Neon is another example. That first level is filled up with its 2 electrons, and the next energy level can hold 8, and that's exactly how many it has, 8. And so neon is stable. Argon is another example. It has its first 2 energy levels all filled up and its third energy level filled up. But if you hop over to an element like lithium, for example, lithium has its 2 electrons in the inner level, so that's all good. But then its next level should have 8 electrons, and it only has 1. So lithium has a problem. Nature does not like this sort of arrangement. It wants the electron energy level to be completely filled in its outer shell. And so lithium has to do something. It either has to gather 7 electrons from some source, or it has to kick the 1 electron that's extra out. Is it easier for lithium to gain 7 electrons or to kick out 1 electron, do you think? Yeah, as you might expect, it's easier for lithium to kick out that 1 extra electron. And so it does. If you look at fluorine, for example, on the other end of the spectrum, fluorine has 7 electrons in its outer energy level. Fluorine has 2 choices. It can either gain 1 electron from somewhere, or it can kick out 7. All elements want those outer shells filled up like the noble gases so that they're stable in nature. And so fluorine's choice then would be to gain an extra electron. So here's what happens. If we take lithium and fluorine, for example, lithium might be floating around next to a fluorine, and lithium's like, hey, I got this extra electron. Does anybody want it? And fluorine's like, heck yeah. So fluorine will gain that electron, lithium will kick that other electron out, and they'll both be good. Lithium will have 2 in its outer level, and that's how many it needs to fill that up, and fluorine will have its 8. The problem with this is that lithium needs 3 electrons to balance the 3 protons in its nucleus, and fluorine needs 9 electrons to balance its 9 protons in the nucleus. When fluorine gets an extra electron, now it has 10 electrons, and 1 minus charge is left on its own. And the same with lithium in the reverse sense, in that lithium has 3 protons but only 2 electrons. So lithium then carries a positive charge, and fluorine carries a negative 1 charge. So lithium with a positive 1 charge and fluorine with a negative 1 charge, once they give up their electrons, all of a sudden, they're electrically attracted to one another. Fluorine and lithium then bond chemically. And so that's how bonding works in elements. An example, a different example here. We have sodium and chlorine. When sodium loses its outer electron, it becomes a +1 charge, and when chlorine gains that electron, it becomes a -1 charge. When an atom carries an electrical charge, it's called an ion. Sodium then would be a positive ion, and chlorine would be a negative ion when they gain or lose their electrons. When that happens, they carry an electric charge, and those ions then are attracted to one another and really come quickly and bond together electrically. This then, because two ions bond together, are called ionic bonds. Here's sodium and chlorine from a different perspective here. Sodium giving up its extra electron, chlorine accepting it. When that happens, they're electrically charged or electrically opposite. Opposites attract, and so they chemically bond together. Ionic bonds are very strong bonds, and they form ionic compounds. There's one other way for elements to bond, and that is in the way in which they can share electrons, and this is called a covalent bond. Co meaning together and valent meaning electrons. They are sharing their electrons with one another. Water is a perfect example of this. Water is one oxygen and two hydrogens. The hydrogens need one more electron, and the oxygen needs two more electrons. Hydrogen, though, can't give up its electron. It can't just be a proton floating around out there. And so what happens is that two hydrogens come to the oxygen, and the hydrogen will share the one electron it has with oxygen, and oxygen will share one of its electrons with hydrogen. And so hydrogen overall feels a net electron configuration of a that it gains the extra electron it needs, and oxygen gains the extra electrons it needs by sharing. And so covalent sharing these bonds. Chemical bonds that are sharing between elements are not as strong as when you have an electron exchange, a complete electron exchange. And so as a result, these are weaker bonds. But these covalent bonds form elements brought together. In any sense, whether you have a covalent bond or an ionic bond, a molecule is formed. And this is how our elements come together to form molecules, which form our minerals. So let's discuss then the definition of a mineral. Now, minerals have a different definition in geology than they do, say, in pharmaceuticals. A mineral, when you're looking at vitamins and minerals that take into your body, have a little bit of a different definition than what a mineral from a geologist's perspective is. But a mineral is a naturally occurring entity. It occurs in nature. Nature forms it. It's inorganic. It's not carbon-based. It's not grown. Anything that can't be grown must be mined, and so inorganic is a qualification of being a mineral. So a plant would not be a mineral. Actually, coal is formed from dead plants. That would not be a mineral. Coal would not be considered a mineral. It has to be solid. It can't be liquid or gas. So water can't be a mineral, or the element mercury can't be a mineral. Molecular oxygen that floats around in the air cannot be a mineral. It's a gas. It also has to have a definite chemical composition. It has to have molecules, like we talked about earlier, particular elements bonded together to form a repeating chemical formula, like SiO2, for example, and silicon dioxide, or NaCl, like we talked about earlier with halite. We see a picture of halite there. The sodiums and chlorines come together and in a definite repeating pattern. And it does have to have a crystal structure pattern, an orderly arrangement of those atoms. So we have the sodiums and chlorines bonded together, and they actually end up making a cubic style structure, and that's how they fit together best. And so the outward appearance of halite is also cubic. In fact, broken up pieces of halite are also cubes. When you shake salt onto your food, if you looked at that with a magnifying glass, you would actually be seeing little cubes. Let's test our definition of a mineral with a few substances. First of all, glass. Is glass a mineral? Well, it occurs in nature. You're looking at a picture of obsidian there. Obsidian is volcanic glass, and it is solid. The thing about glass is sometimes its chemical composition varies. You can have pure silicon glass, but the problem is that it doesn't have a crystal structure. Glass actually forms from molten material cooling extremely quickly, and when it does that, the elements don't have time to arrange themselves in their crystal structure. And so, you know, quartz on the left there is a nice repeating arrangement of crystals, a pattern making a crystal structure, whereas glass on the right there has all the elements, but they didn't have time to set up in a crystal lattice, and so it's kind of called an amorphous solid. So glass is not a mineral because of this. In fact, you can see in old houses or old windows, you can see wavy glass because the glass is actually flowing. It's drooping because its crystal lattice is not strong enough to keep its form. Glass then is not a mineral. Ice. Is ice a mineral? Well, let's take it through our definition. It is naturally occurring, obviously. It's solid. It has a definite chemical composition of H2O, and it does have a definite crystal structure. If you've ever seen a snowflake, of course, the H2Os arrange themselves into some pretty beautiful geometric shapes. Thus, ice is a mineral. Water would not be a mineral because it's liquid, but ice is a mineral. Let's talk about the different groups of minerals and how they're used. We know that, of course, minerals are used in gemstones, things like diamonds, emeralds, rubies, sapphires, etc. But minerals have many various uses minerals are also used in everyday products and everyday things that we use, such as our homes, for example. Paints have kaolinite in them as part of the pigment. Our pipes have copper and steel and lead. Walls are made from gypsum, which is the drywall that we have. That's actually a mineral in between two pieces, in between paper. Kitty litter is a type of clay mineral, smectite. They also use clay minerals in detergents as surfactants. Foil is from the mineral bauxite, and that's where we get aluminum foil. So there's many applications of minerals and uses of minerals. The variety of minerals we see depends on the chemical elements available to form them, and as we noted before, the most abundant elements in the Earth's crust are oxygen, silicon, aluminum, iron and magnesium, calcium, potassium, sodium. Those are the main ones that make up most minerals on the Earth's surface. In fact, there are 3,000 known minerals. Only 20 of these minerals are common. So because we only have a certain number of common elements in the Earth's crust, only a certain number of minerals form. The most abundant and most common minerals on the Earth's surface are those based on the silicon-oxygen tetrahedron you see pictured there. Remember I said that when you take oxygen and stick it together into a pyramid shape, silicon fits perfectly in the center there. That silicon-oxygen base provides the base for most rocks on the Earth's surface, and these are called the silicates. 96% of all minerals on the Earth's crust are silicates. This is the most common mineral group. And there's a stable form pictured there. Pictured on the right there is the mineral quartz. It's repeating units of the silicon tetrahedron. There are other mineral groups. Carbonates are made from calcite, which is calcium carbonate. These are the remains of once living organisms. Halides are things that come from evaporated material, things like salt. Rock salt is NaCl. Native elements also constitute minerals. Copper, gold can be minerals. Oxides are minerals that have the base of oxygen. Hematite is one example. Sulfates and sulfides are sulfur-based minerals. Gypsum is an example of a sulfate, and a sulfide would be like pyrite, which is called fool's gold. It looks like gold, but it's actually much harder, and when you powder it up, it turns black. Of the 3,000 different types of minerals, there are about 20 that we see in most rocks on the Earth's surface, and 10 10 minerals really make up 90% of the Earth's crust. These are our silicate minerals. These are quartz, orthoclase, plagioclase, and muscovite, biotite, calcite, dolomite, halite, and gypsum, and ferromagnesians, including olivine, pyroxene, and amphibole. These are the most common minerals that make up most of the Earth's crust. And so if you see a rock, it's likely got one of these minerals in it. All right, well, I hope you enjoyed our tour through minerals from the very beginning stages of matter, the atom, how different isotopes form from that, looking at the periodic table and the different elements out there, particularly there are 8 specific minerals or 8 specific elements that make up most of the Earth's crust, and how that matter then combines to form those minerals that we see out there through chemical bonds. We looked at the definition of a mineral, some of the uses of minerals and groups of minerals out there. There's one more aspect of minerals, and that is the physical properties of minerals and identifying minerals, and we're going to go through that in a different section through the homework. So thanks for listening to Minerals. I hope you have a great day.